take a look at a real-world example where we can see solving polynomials in action. So a company is designing a new box for shipping where the length is 4 feet greater than the width and the height is 1 foot less than the width. The volume of the box must be 12 cubic feet. The question is, what is the width of the box? So first of all, let's draw a little picture. This is not at all drawn to scale, but let's just sort of draw something here. And so I'll call this the width. I know that the length is going to be 4 feet greater than the width. So that's going to be 4 plus the width. And I know that the height is going to be the width minus 1. So this is going to be W minus 1. And I know the volume is going to be 12 cubic feet. That means length times width times height. So in this case, that would mean W times 4 plus W times W minus 1. That has to equal 12. And I now want to solve this. So how do I solve this? Well, I first multiply all this out. And so I'll see W times, and here I'm going to see a 4W, and then I have minus W is 3W. And then I see W squared, and then I see a minus 4 equals 12. If I distribute, what I see here is a W times W squared is W cubed. And I see W times 3W is 3W squared. Negative 4 times W is minus 4W. And then please allow me to subtract 12 from both sides. And so I see minus 12 equals 0. So now that's the equation that I have to solve. And that's a cubic. It looks pretty scary. I'm not liking it. So what do? What we do is we use the rational root theorem. The rational root theorem says if there are going to be any rational roots at all, then we know that they're going to either be plus or minus factors of this number, the last constant number, divided by plus or minus factors of the leading coefficient, which in this case is 1. So what are the possible rational roots? Well, plus or minus 1, that's a factor of 12. Plus or minus 2, plus or minus 3, plus or minus 4. These are all factors of 12. Plus or minus 6. And, of course, plus or minus 12 itself. And that can be all those numbers divided by the possible factors of this invisible 1, which are just plus or minus 1. So, in fact, they don't really add anything. So we've got 2, 4, 6, 8, 10, 12. 12 possible numbers to check, the plus or minuses of all these. And so which ones might be solutions? Well, what we can do is we can actually use a graphing calculator to graph the function y equals this and see how many places it crosses the x-axis, or in this case the w-axis, and then see which one of these seems to be close. And when we do that, what we see is that, a couple of them are close. We see that 2 is going to be, so here are the ones that we see are close. So close. We see 1 happens at 2. And if you look closely, we see 1 also happens at negative 3. And 1 happens at negative 2. So if you look at the graph, you can see that we seem to be crossing around there. Now we can check to see if, in fact, they really are roots by using the fundamental fact that 2 is a root if and only if x minus 2 is going to be a factor of this. W. W minus 2 is going to be a factor of that. Similarly, if W minus negative 3 is a factor and W minus negative 2 is a factor. So all we have to do is either long divide out by this into this polynomial, or we can use synthetic division. Either way, and we can check, and when we check it, we see that, in fact, this factorization holds. That if you take this times this times this, that actually equals this polynomial. So when we set this equal to 0 and solve, we see we have 3 solutions. W equals 2, W equals negative 3, and W equals negative 2. So are there 3 answers? Well, no, because W represents a width. That means that it's actually positive. So we throw away these for this context, and we see that the width has to be 2 feet. 2 feet.